the LIGO Scientific Collaboration. Thank you. And he's an expert in numerical relativity and especially intermediate mass black holes, which we're going to learn about today. And conveniently, they've been in the news recently, so I'm even more excited than I would be otherwise to hear about it. In addition, Karan's received a number of accolades and awards along the way. He's a recipient of the Sam Nunn Fellowship, a Postdoc of the Year Award from Vanderbilt University, and the Forbes 30 under 30 scientists list. So we're really very lucky to have him today, and we look forward to your talk. So Karan, you can go ahead and share your screen directly.
Let's see if I can.
Fantastic.
Sure. Well, first of all, thank you so much for having me here at ITC. It's been a real honor.
Oh, can I interrupt? Sorry. I will play a bell sound when there's about 5 minutes left.
Okay. All right. That's fine. Okay. So yes, thank you for having me. I think it's just happens to be a very timely topic and talk that I'm excited to share. Just last week, we announced the detection of a new gravitational wave event. LIGO and Virgo have announced a number of gravitational wave events so far, each breaking one record over the other. But this one is close to, personally to me, because this has been one of my main roles within the LIGO collaboration. And it's also a very unique astrophysical source. So I hope in the next 10, 20 minutes, I'll be able to convince you on the same. So those who are catching up with this news, on May 21st, 2019, we sent an alert that there was a signal detected by the LIGO and both LIGO detectors in the United States and the Virgo detector in Europe. Those who have signed up for this gravitational wave triggers, if you have the app, you will get a notification on your app whenever a signal is sent. The signal, we release the sky map, and I'll talk a little about how other astronomers have followed sky map, but they typically this is to aid electromagnetic follow-up. Just last year around this time, I was at Harvard visiting the physics department and also the ITC, and was by this September of last year, an editorial team had been formed to start describing what this discovery is. It took us about 15 months to finally announce that we have seen what we have seen on September 2nd, 2020. Back then, when we had started working on the paper, it was this thinking that an exciting press conference would await, where we would be able to say this with much fanfare. As the time it is, we announced it over a Zoom call just like this. But yet it was still a press release. The announcement happened from the European Gravitational Wave Observatory with the partners from the Virgo collaboration. I was the representative there on behalf of the LIGO Scientific Collaboration, which constitutes of about 90 universities from 18 countries. The three colleagues of mine, we three were part of the editorial team that published two papers that were released on September 2nd. One was published in the Astrophysical Journal Letters describing the astrophysical implications of the source, and the other was published in the Physical Review Letters describing more sort of the discovery. And there's a lot of things which has been covered in these two papers, which I would not have, unfortunately, time to chat, but we can discuss more over Slack. Though if we had to summarize the discovery in perhaps one sentence, is what the New York Times had on its cover story, that these black holes shouldn't exist, but there they are. And I think that is one of the reasons I would, if in retrospect we look, it took us a while because we had to do a series of confirmation, almost unusual for all other gravitational wave events we have seen till date. Just because of the claims that we were getting were so quote unquote wild. One more thing I liked especially about this, the Times article is they did not use an artistic depiction of what these black holes were, but an actual solution of Einstein's equation. This abstract simulation was from our group. You can see what we actually detect is not any light around the two black holes, although those are the more famous pictures. We also don't see any gravitational wave lensing around them. All we see is just the one-dimensional version of the three-dimensional gravitational wave, which is released. The other thing here, I just want to, because it's something which is missed usually, is the size of the event horizons, which is placed here, is the actual size of the two black holes compared to the gravitational wave amplitude. So the fact that we see this few 100-kilometer wide objects from literally halfway across the universe, it's just by itself so mind-boggling. So what makes this particular discovery challenging was the very gravitational wave morphology. This is the shortest signal we have seen in the LIGO and Virgo detectors till date. The overall signal only lasted about 0.1 seconds. And that is because LIGO is sensitive in a particular frequency band, and the heavier the black holes, the lower the gravitational waves frequency they would emit. So we only saw about 4 cycles beyond the 30 hertz limit that, once the detector is in its sensitivity band. You can see the picture on the left is this plot that is usually released with all gravitational wave discoveries. The yellow line there is what the solution we get from the Einstein's general relativity. The blue line or the purple line is if we want to reconstruct the signal without assuming any model, like completely independent morphology. Yet we can see this signal has a false alarm rate of about 1/5,000 years. So we know this is not a background noise of any sort. The event was particularly seen by what we call an unmodeled burst search, because if you see this time frequency map in the bottom panel, you'll see it's a blob. It's not like the usual curve that we tend to see in gravitational wave. It's literally a blob, and this is what we'll search for in the data. This is particularly powerful to look for very massive black holes like intermediate mass black holes. Part of my PhD thesis was to train this kind of a search. We've been using this. I've been particularly running this even before LIGO made its first gravitational wave discovery. So over the time, the search has really evolved. We have done a full search for intermediate mass black holes since every observing run of LIGO. I was one of the lead authors on those papers as well. And the fact that we did not see it, all this now, makes this event particularly rare. We had already set astrophysical upper limits on this class of black holes. The current rate is we would see only one such event in every 8 years in a cubic gigaparsec volume, which is 500 times less than what you expect for regular binary black hole mergers that we have seen till date. Also a fun fact, 2 signals were detected on that day, just 4 hours apart. Before theorists want to make any claim, those two are absolutely not related. We have looked around and they come from different parts of sky, but the universe was particularly generous on May 21st. Now, the striking feature of this discovery is the masses are unusually high for the 2 black holes. We have used 3 state-of-the-art general relativity signal models that can have the gravitational waveform from a binary black hole coalescence, that is the inspiral, merger, and bring down. These models take into account all possible systems, including the precession of the orbits, the gravitational radiation beyond the quadrupolar term. Some of the most evolved analysis we have done for any event till date. We further compared with 3,000 above numerical relativity simulations, like the first visualization that I showed from the Times video. Each such simulation is about 50,000 hours of computing times on some of the world's fastest supercomputers. We had the resources because over the time, many such catalogs have been made public, including one that my group and I published in 2016. All of this consistent analysis later, we can confirm and say that both primary and secondary black hole that make this collision is heavier than anything we have seen so far in gravitational wave astronomy. The plot on the left gives you a representation. 3 models, 3 contours refer to what 3 models think the masses of the 2 black holes are. X-axis being the bigger black hole of the 2, the y-axis being the smaller, M1 and M2. The red triangle I've drawn just as for reference. This is where all the LIGO black holes, LIGO-Virgo black holes would be that we have seen so far, under that triangle box. So this really stands out. Now, a thing which I want to specifically mention here is in most work, I mean, through press release or otherwise in abstract, we would quote that the mass of black hole is 85 and 66, which is the median value of what we get the mass. But everything that is within the contour is consistent with the signal. So if you have a model that says a black hole should be 60 solar mass or 100 solar mass, well, we find both of them to be consistent. The median values favor a certain value. I just want to highlight on that part. We further think that the binary is fairly equal mass. So that tells us a bit about its formation channels. So while we do the analysis, we are oblivion to any astrophysics. We don't take into account any astrophysical modeling of what the source is. But the implications of why this was such a big deal is that the two black holes that collided are in what is called the so-called pair instability supernova mass gap. The idea is somewhat reflected in this plot. So if you had a star and that collapses and forms a compact object during supernova, there is a certain mass loss that will happen. So if you had about a 20 solar mass zero age main sequence star, it would form a 5 solar mass black hole. The higher the zero age main sequence star is, the size of the black hole would depend on the metallicity. So the low metallicity stars would end up making bigger black holes. What we find here is that provided this recipe of pair instability, which softens the equation of state and creates this electron-positron pair at the time of supernova, so it leaves no remnant behind, that we should not expect anything in that certain mass gap. These two black holes have a high probability of being part of it. You can see that the violin plots on the left panel are that the two black dots are what the black holes, primary and secondary, were, and the red is what happens after merger. The only other way we could have formed it if there is no pair instability is one of the earlier triangles makes this black box again. If you compute the probability, the secondary black hole, I mean, the pair instability limit is fairly vague. We don't know where it starts, whether it starts at 50, whether it starts at 65, what it is if the binaries, the stars are born as binary. But roughly it could be anywhere from 6 to 46% that the smaller black hole is also in the pair instability mass gap. So that's a major conclusion we get just from the masses of the system. The other evidence we have is for the spins. Now it's a sort of interesting that we only see 4 cycles, but the way gravitational wave morphology is, it's so sensitive to many things that is internal to to the event horizon. So if the event horizon is spinning, because both the black holes are curved black holes, it leaves a particular morphology in the signal. We find mild evidence that both the black holes exhibited spin orbit precession just before the merger. Now, why it is interesting is then that means maybe the black holes were dynamically captured, and that's why their spins are not aligned with the orbital angular momentum of the axis. The plot on the left is the sort of a spin disk plot we show to tell where the spins of the two black holes are. We even looked at the evidence that what if the system is not spinning at all? We find strong evidence that the system is spinning for sure. So those are the quick things on spins. Now comes the most interesting part to me, which is that the merger has produced, when the two black holes collide, it releases intense gravitational wave. This one releases 8 solar mass c² of gravitational radiation, making it one of the most energetic events in the universe since Big Bang. It is definitely the most energetic event in gravitational wave astronomy. So the final black hole is smaller than the total mass, but it is still above 100 solar masses. It's about 140 solar masses, making it the first direct observational evidence of intermediate mass black hole. And I have to put an asterisk here because the definition of intermediate mass black hole is perhaps from gravitational wave side is different, because LIGO is not sensitive to the 10,000 solar mass intermediate mass black hole that the astronomy community is more used to. But still anything above 100, I think we can now start calling light IMBHs, if not IMBH to begin with. The other thing we can infer is that the black hole is spinning at about 72% of its theoretical limit, the final black hole. We have also measured the ring down. This is the only second time we have seen one of the ring down modes. We have inferred the mass independently and we get the same answer in ballpark. Moving on, this is the farthest gravitational wave signal we have seen. The redshift can be anywhere from 0.5 to 1.1. There is a strong impact. Oh, the bell has rang. One thing I would say is there is a claim for an electromagnetic counterpart by the ZTF team. The masses that, the distance that we get is at least twice farther than that. There is one model that has a mild evidence, but I can speak about it later. Is this the only intermediate mass black hole we have seen in LIGO so far? Well, no, we have seen other candidates. They are not as dominant as this signal is, but another one, GW17502, that one of my undergraduate students and we published, which was also released on the same date, September 2nd, has a mass that is roughly about 157 solar masses. There has been other independent events confirmed, published by the Princeton group, by the Syracuse group. They find events in LIGO data, which LIGO does not consider, the same significance level, but they exhibit black holes that are definitely above 100 solar masses when they form after merger. Now, I promised this last slide. What does this mean for gravitational wave astronomy in future is that the next generation of instruments would get better at low frequencies. The lower the frequencies, the higher the higher the binary black hole mass we can see. So this plot is one of those defining plots of gravitational wave astronomy, that the y-axis is a redshift in log scale. The x-axis is it's the total mass in log scale. We can survey everything from subsolar mass black holes to stellar black holes to intermediate mass black holes and supermassive black holes in the scale of next 15 years. The different contours refer to the different epoch of gravitational wave astronomy, new instruments that would come. The blue curve is the space mission LISA. That is particularly sensitive to the higher size of intermediate mass black holes. And the other curves on the left refer to ground-based detectors like Einstein telescope, which would see the lower total mass. But we would be able to survey practically every intermediate mass black hole in the observable universe in coming years. This was published as the cover of the Nature Astronomy. Please feel free to read it more about it. The last part is then, do we see such signal in LISA? Yes, we do see the same system in LISA, and that opens something called a multi-band astronomy. It is different than the multi-messenger astronomy, because in multi-band, you look the same way that a radio and X-ray telescope can see the same source together. Here you have two gravitational detectors, different frequency bands, can see the same source together. So the plot on the left is a joint volume of the two different sensitivity band. So LISA starts seeing this very signal about 4 or 10 years before its merger. And why it is so crucial is that we don't know if the system is eccentric. We don't know what the spins of this, exact spin magnitudes of this are. But if we start seeing the system 8 years before, those morphology will be very strongly impacted by this environmental parameters of the system. We expect about 8 to 30 such sources that LISA would see. So that's very promising science case that the detector offers. In interest of time, I'm going to move on from the multi-messenger part. So I just want to end on this note, which is an open question, that what then makes this signal? I'll say there are two things, two classes that I define. One is astrophysical, that is standard astrophysics can make it, and the other is more exotic. The standard astrophysics, can this be stars? Can stars not go through pair instability supernova and still make this black holes? So calculation about this, Professor Lobe and I had done last year, and we find that less than 0.8% stars could make what these black holes are. Can these black holes be mergers of previous generation black holes? So can the first gravitational wave detection find another black hole and merge again? Yes, maybe. The probability is very low for two reasons. A, the black holes, of course, have to be in a very dense environment to do so. But every time a merger happens, they get kicked away with a high recoil velocity. So you need something to keep them glued in the globular cluster. This can happen if the stars have been colliding in some sort of a runaway fashion in the young globular clusters. We have discussed that rate too. We find about 8% of stars would end up doing this mass if that is a channel. Now there is another prominent channel which is forming this black hole in the AGN disk. So these are not per se a standard stellar method. I would have put it in exotic, but now there is a growing community of people who are working on this model, so it has become very mainstream. A strong claim is a possible electromagnetic counterpart, which has been associated with this very event. So that is something in future to look out for. Can we rule out exotic things? Can this be a core collapse supernova? Very unlikely, because A, the morphology does not match, and the amplitude of signal that we have seen, for that to be a supernova, we would have also seen some other counterpart like a neutrino signal. Can this be cosmic strings? We looked into it, we did an extensive test, and the data does not favor cosmic strings at all over a binary black hole merger. Can this be beyond general relativity? Can this be not binary black holes that Einstein's theory predicts? We looked at the residual in the signal. So you subtract what is the best matching Einstein's solution to this signal and look at what is left. And we don't find any evidence for non-GR at the moment. Can this be strong gravitational lensing? Again, unlikely. The data does not support for various arguments that we have presented in the paper. The two things which we cannot rule out is, can this be primordial black hole mergers? And very well it can be. The spin is still fairly broad. You could think the primordial black holes may not be spinning as fast as a hierarchical black hole merger, or the ones that have formed directly out of stars. So there is an evidence, and this comes from fairly far away. If the merger happens at redshift 1, that means the binary has happened much, much earlier. So that exists. Can this be a highly eccentric collision? And we have not seen eccentricity because the signal is so short. Very possible. The reason we cannot do much about it, even if we were knew this scenario, is that it's hard to model gravitational waves with generic eccentricity. So this is the open things. But what in conclusion I can say is that this mass range, 100 to 1,000 solar mass, is perhaps one of the most exciting astrophysical sources in gravitational wave astronomy for the next 10 to 15 years, because all detectors would be seeing this source. Unlike a binary neutron star, which only few space detectors cannot see, this one is pretty much common across gravitational wave experiments. So I hope we are able to at least check some of these models in coming times. Well, thank you so much for the patience. Okay, let me stop my.
Thank you so much for this great presentation and also very exciting result. Maybe to start the questions, and I don't know, maybe you can still use your slides if it helps you. So Flora Brogarden had a question about the highly eccentric merger. Yeah, she noted that there have been recently several groups discussing that the event is perhaps better matched with an eccentric merger. Can you discuss what parts of the LIGO data analysis might hint to this? Oh, you're muted.
Okay, can you hear me now?
Yes.
Yes. So as you can see in the signal itself, this morphology is fairly tight. We only see 4 wiggles. But if you see the black line, which is a reconstruction of from a different search, there is something before the peak and after the peak that goes for multiple wiggles. In that, if we try to fit an eccentric merger, it may. I'm not saying it cannot. But at this point, the degeneracy is so high with this one signal that it is, any claim would be very under quote unquote caveats for eccentricity.
Okay, but so, and then the signal is really in this kind of outskirts that are kind of noisy. So I had a maybe related question of kind of teasing out the signals, or as much as we can out of this. So it feels to me as a non-expert that the contour lines in the mass plane are kind of wider than what we are used to in for other LIGO sources. So I was wondering, is there how can we do better in providing more precise mass estimates for these systems?
So there are 2 things that here determine the mass. So the mass here that I reflected is the mass in the source frame. So when we see the gravitational waves, it has been redshifted. So we first have to assume a cosmology, and then we find the redshift corresponding to the luminosity distance. And then we get the mass of the black holes in the source frame itself. So the error in distance usually ties in the errors what we have in the mass itself. One of the things then, let me just plot the distance plot. So here again, you can see the distance is fairly broad. we were able to break, there is a degeneracy on the inclination of the binary and the how far it is. If it is head on, if it's edge on, we see the system has to be much closer. We use gravitational waveform that had what you call the beyond quadrupolar turns that allow radiation off axis, not perpendicular to the orbital plane, but much more involved geometry. Because of those, we were able to break the degeneracy in eccentricity, at least for the two of the models, yet not much at this stage of the models that we have, the level of signal it is. The expectation is that if we see a lot more of this, at least some of them would be at a higher signal to noise ratio. This one has a signal to noise of about 15. If you compare with the first detection, which had a very tight masses, that was about 24 signal to noise.
Oh, I see. That would make a difference. I guess shifting a little bit our topic of discussion into the kind of the origin of these Munoz has a question of how likely would you say it is that this black hole is the result of a previous merger? And what would that tell us about the possible hierarchy of merging black holes?
So we did compute the probability that can it be a second generation merger of some sort, and the inferences we would get is in the spin itself. Because if it's a second generation, then the spin of the black hole has to be greater than 0.7, close to 70% of the theoretical limit. What we, in this coming up study, I'm just going to flag it here. We have looked at all the heavy black holes that have been seen in gravitational waves so far, not just this event, but the other ones too. And we try to make a fit with a spin parameter, which is this emergence spin. It's a sum of the two black hole spins combined. And on the x-axis, you find the mass of the primary black hole. We can fit it. The data at least supports this kind of a fit where you start with at least 0.7 spin to begin with as you increase the total mass. So once you are in this pair instability mass limit, the black hole spin seems to be slightly higher than the lighter black holes that we have seen. You can see the distribution is fairly broad. Spins are very tough to constrain from the system. But this is where we need something like a LISA mission essentially to help.
That's Morgan had a kind of follow-up question on the LISA threads saying, so that's Morgan McLeod. I'm assuming that the LISA detection would constrain the eccentricity. Can you talk about what a multi-frequency detection would constrain for us?
So the two things that LISA would be able to constrain, one, so more directly, we would have a hint on the merger time from LISA. So assume, let's say that these black holes have formed in an AGN disk. So there is gas and radiation around these black holes, which would influence its evolution versus if it is in a vacuum. So in principle, you could place this black hole much closer than you would have done in an isolated environment. This signature is reflected in LISA because the gravitational strain would follow a different slope. Your separation is different, so the gravitational wave emitted has a different slope. We would be able to test this in LISA right about. We can't really do much in LIGO band because by that time the system has become almost circular, almost vacuum around it. But yeah, so this is just one plot of merger time versus separation for different channels. And the eccentricity would also be somewhere here and would have a very distinct path.
So maybe just as a close, to close up here, what resources do you think we should be starting to get ready to be able to follow up these possible LISA detections?
So the most important challenge we have right now in LISA detection is to get the waveforms that we would need to study this system. We recently published another study where if you use the current simulations we have and the level of signal to noise you see in LISA is about 1,000, minimum 100 to 1,000. So what happens is your numerical errors of this very simulation of solving it is as good as any of the non-GR effects that we are trying to find. And just not non-GR, even if the system is processing or so, those effect gets confused just with the numerical noise now. So one big study perhaps, that needs to be done over the time by the community is get gravitational wave signal models that work in LISA. And because we are still 15 years from that, we can take a little break. But still, this is something very urgent in terms of development.
Okay, awesome. Well, thank you so much for this exciting update. We'll be looking forward to how the story develops, so that you also have the paper in prep is for Nature submission. So yeah, we hope to be able to invite you again soon to tell us more about it.
Well, thank you so much.
Thank you. Yeah, thank you for a really interesting talk. So allow me to introduce our second speaker, who as a member of the CFA needs sort of very little introduction, but Karan Zucker will tell us about some of her recent work. Karan is a postdoc now at the Center for Astrophysics. Previously, she received her PhD this past May 2020 from Harvard. Where during her thesis work, she was advised by Professors Alyssa Goodman and Doug Finkbeiner. She is sort of a world expert on mapping the much more local universe, our part of the galaxy, in 3 dimensions, and pulling in all of the constraints we can to better understand our place in the galaxy. During her time as a graduate student, she received and was supported by a number of fellowships, including by the National Science Foundation Graduate Research Fellowship. But without further ado, Karan, we're excited to hear what you've been up to recently. Thank you.
Thank you, Morgan, and thank you, Anna, for inviting me to be here. Let me just share my screen really quick.
Oh, and I'll play that bell when you have about 5 minutes left.
Okay, sounds good. Okay. Can you see my screen? Yep, okay. Okay, so thanks again, Anna and Morgan, for inviting me to be here. I'm very excited, albeit virtually. And today I'm going to be talking about 3D dust mapping in the age of Gaia. And so I'd just like to give many thanks to my many wonderful collaborators you can see listed here, without which this work would not be possible. Without further ado, 3D dust mapping in the age of Gaia. So 3D dust mapping in the age of Gaia involves combining Gaia data with large photometric surveys and new computational and statistical techniques to map out the 3D distribution of interstellar dust in our Milky Way galaxy. And so this could take up many, many hours, but I just want to preview for this talk 2 of the main results that have been obtained using 3D dust mapping in the Gaia era. And so one of them is going to be on kiloparsec scales, and then we're going to zoom down into parsec scales in our solar neighborhood. So on kiloparsec scales, I'm going to show new results on the 3D spatial distribution of nearby star-forming regions obtained with 3D dust mapping. And particularly, I'm going to present the discovery of this structure that you see right here in red, which is called the Radcliffe Wave. And each red blob is a star-forming region whose distance has been accurately measured in Gaia. And so this structure was not known before the rise of Gaia, and in particular is very interesting because it's incredibly linear when you see it from top down, but it undulates with respect to the galactic plane when you see it from the side. And so we think that this structure is actually a dense spine of the local arm of our galaxy. And so I'll start with the Radcliffe Wave, and then by the end, we're going to actually zoom down into individual star-forming regions inside the Radcliffe Wave. So resolving the structure of individual molecular clouds that are forming in this much larger swath of the spiral arm. And so for people who study star-forming regions, you might think that this little cutout that I show here is actually a simulation, but it's not. It's actually a 3D view of the dust in a local molecular cloud, the Perseus molecular cloud, at 1 parsec. And so the reason why I think this is so exciting, in particular for the theory and computation colloquium, is because really for the first time, we're able to resolve the 3D structure of our galaxy on scales comparable to numerical simulations at large dynamic range. So from swaths to spiral arms all the way down to individual star-forming regions inside molecular clouds. And so you can begin to test from both a theory and an observational perspective how things like galactic dynamics, stellar feedback, magnetic fields, the gravity of the gas, how that shapes star formation in molecular clouds and how that shapes the star forming history of galaxies like our Milky Way. So before I get into the meat of the results, I just want to show briefly how 3D dust mapping actually works and how it got a huge distance resolution boost from Gaia. So say that we have a star and we observe the star in our galaxy. So we have broadband photometry for billions of stars in our galaxy. So we have knowledge of the colors at optical and infrared wavelengths from surveys like Pan-STARRS and 2MASS. And if there was no dust between us and the star, that star would appear yellow to us. And it's intrinsically yellow. However, we know that if there's a dust cloud between us and the star, the colors of that star will be reddened. And so you can see that very clearly in something like this nearby dark cloud, B68, where on the outskirts of the cloud you have this reddening effect, and then that's not true for stars not along this dust cloud's line of sight that are in the background. And so in reality, we have billions of stars scattered throughout these dust clouds in our galaxy in 3D. And how reddened those stars will become will depend on whether they lie in front or behind the dust cloud. So stars behind the dust cloud will appear more reddened than stars in front. And so what you can essentially do is bracket dust clouds between these two types of stellar populations. So in reality, this is much more complicated, of course, as everything is. So these stars have different intrinsic types. You have to model the type of the star. So dwarfs and giants will have very different colors. You have to model the distance of the star, and you have to model the amount of dust between you and each star. But if you can do all that, and with new computational and statistical techniques, you can infer the cloud's distance and thus the 3D distribution of molecular clouds from the dust effect on stars. And so you can do this entirely without Gaia, but when you actually add in independent constraints on the distances to stars from Gaia, you get a huge distance resolution boost. And so you can resolve these clouds in detail. That was a detailed view of these clouds that was never possible in the pre-Gaia era. So what does this actually look like in practice? So this is what this inference looks like. So this is essentially showing you what the dust, how the dust varies as a function of distance along 3 sight lines in our galaxy through local molecular clouds, so through famous star forming regions. And so on the y-axis, this is the integrated amount of dust along line of sight, so integrated extinction. And on the x-axis is the distance or distance modulus. And then each of these red crosses are marking the position, the distance and extinction to individual stars along some sight line. And so you'll see in the foreground that there's this de-reddened, unreddened foreground population nearby. And then there's this reddened population of stars at farther distances. And so you know that the cloud has to lie between these two populations in order to produce the colors that we observe for the stars. And so this is actually the pre-Gaia version of these plots. But once you actually add in independent constraints in the distances from Gaia, you get a much sharper view of the distances. And you're going from uncertainties on distances of like 25 to 30%. And distance uncertainty is down to about 5%. And so you're improving on the distance estimates by a factor of 5, which allows you to reveal the existence of new structures in the galaxy like the Radcliffe Wave. But don't take my word for it. So we're going to actually compare our distances obtained via 3D dust mapping with the gold standard for star forming regions in our field. And thankfully, the people who have produced these gold standard distances, I think, are both on this call, Mark Reed and Tom Dame, who have led the Bessel survey here at the Center for Astrophysics. And so what we've done is we've compared sort of the gold standard distances to star forming regions from Bessel. So maser parallax measurements towards high mass star forming regions with our dust-based distances in the era of Gaia in regions of overlap. So you've probably seen a plot that looks like this. This is the maser view of our galaxy. So each of these different colored points are showing you high mass star forming regions along different arms. So this is the galactic center, this is the sun. And so we're going to essentially compare with all the masers in our solar neighborhood in cyan along the local arm. We find really good agreements. So we agree with the gold standard estimates to within 10%, and we find no systematic offset out to 2.5 kiloparsecs, which is great because even though masers are the gold standard and they've informed much of our view of galactic structure over the past 10 years, the great thing about 3D dust mapping is it can be used anywhere where you have dust and measurable stellar properties. So you can essentially fill in the gap with the maser distances using 3D dust distances. And so this is what that looks like. So essentially we target all of the famous nearby star forming regions within 2.5 kiloparsecs. And this is a top-down view of the global distribution of those nearby star-forming regions. So the background grayscale, so the sun's here, and the background grayscale shows the 3D distribution of all the dust in the galaxy obtained by former Harvard PhD student Greg Grains. You can see it on the right-hand side. And then the blue points show just the most accurate distances to the regions that are forming stars. So the blue points show the molecular clouds. And so the two techniques are very complementary, but essentially we sacrifice, using star-forming region distances, we sacrifice angular resolution for distance resolution. And so we're able to constrain the global distribution of star-forming regions to very high precision. And so we see a lot of structure in this diagram. So people who are used to studying the galaxy might note that this is the Sagittarius Carina arm over here, a section of it. This is a very famous star-forming region called the SCO-Sun Association. But what interested us the most is that there's this very peculiar linear chain of star-forming regions that extends about 2.7 kiloparsecs. And it's very straight when you see it top down, but it's even more peculiar when you actually look at it from the side. And so this is this Radcliffe Wave structure that I mentioned at the very beginning. So it's named the Radcliffe Wave because the lead author, João Alves, was a Radcliffe Fellow here a few years ago, and he was frequently was at the Center for Astrophysics. And so we collaborated on this work with many others, and it's now in Nature. And so essentially what we found is that all of the most famous nearby star-forming regions, so regions like Orion or Cygnus X, they're actually connected into one long linear filament with an aspect ratio of about 20:1. It's very crazy. But if you actually look at it from the side, so the side view, and you actually look at how this structure undulates with respect to the galactic plane, you find that all the famous star-forming regions are actually take the form of a damped sine wave with an amplitude of about 160 parsecs and a period of about 2 kiloparsecs. And so we've never seen a structure exactly like this in our galaxy, and it's sort of the largest coherent structure, and we think actually a section of the spiral arm that has ever been mapped at high resolution. And so I actually want to show you exactly how this looks like with respect to the existing models for the spiral, for the local arm based on masers. So I'm going to give this like 10 seconds to load, and you'll get to see a very cool interactive figure of our solar neighborhood. And so specifically what we're finding, and we'll show in a second, is that we think this Radcliffe Wave actually is a dense spine of the local arm nearby. So the 3D view of what I just showed you. This is the top-down view, and then this is the side view. And I want to overlay where we think the masers lie with respect to this feature. So that's what you see in dark blue here. So dark blue, those are the maser positions. Those are high mass star-forming regions from Bessel. And then this blue curve right here, that is the sort of the global fit to the local arm constrained by masers way outside this diagram. But what we're finding is that by mapping not just high mass star-forming regions like with masers, but also mapping lower mass star-forming regions, that we're essentially revealing this very dense spine of the local arm. And that's at least on local scales within the nearest few kiloparsecs, we think that the arm is actually super linear from top down and wavy from the side. And so that's also been observed in nearby galaxies. And so we think that we're essentially revealing this arm at very high spatial resolution. And so there's a few implications here that I just want to go over. So the first that I already touched upon is that the local arm we think is not shaped as we thought it was locally, and that it's straight from top down and wavy from the side. So on large scales, it might look like a log spiral in the plane of the galaxy, but on small scales, it very much does not. The wave's origin is unknown, but it has serious implications for understanding of the star formation history of galaxies like the Milky Way. So there's a couple possible explanations. So one of them is that there could be a collision. So something like the size of the Sagittarius dwarf galaxy could have hit the Milky Way and caused the disk to undulate. But there have also been studies of nearby external edge-on galaxies where they can explain ripples in other disks based on global gravitational instabilities without the need for a perturber. And so what we really need to differentiate between these two scenarios is 3D stellar kinematics, so 3D information on the young stars in the Radcliffe Wave. And so we have a really excellent RU student, prize student actually, who's now working with us this semester. His name's Alan Tu. So hopefully we'll get to the bottom of this soon. And then the final implication is that we find that these star-forming regions that were previously thought to be isolated are actually very much not so. And they're connected by these lower density tendrils of gas. And so it really forces you to rethink our understanding of local star formation in a larger galactic context. And so we have the Radcliffe Wave, and we've characterized the structure of the interstellar medium on very large scales, so on several kiloparsec scales. And so now for the last few minutes of the talk, I want to actually zoom down into individual molecular clouds inside the Radcliffe Wave and understand what's happening on parsec scales in individual clouds. And so this is a view of, again, of like the global view of the dust. So the background grayscale is from Green et al. 2019, it's the dust map, and then the red is the Radcliffe Wave, and the white is the model for the Radcliffe Wave. And so what we're going to do is we're going to pull in complementary results from a very new 3D dust map from Leica, Glatzla, and Enslin 2020. And so essentially what they've done is they've looked at the dust just in the nearest 370 parsecs from the sun. And so this large scale dust map and this smaller scale dust map, they actually use very similar like fundamental unit of inference. So they're both based on this estimates of distance and extinction for individual stars. But essentially they're sacrificing the amount of volume they can probe in the galaxy in order to get increased spatial resolution. And so they've produced this new map at 1 parsec spatial resolution for the nearest 370 parsecs using a Gaussian process-based technique. And so what we're going to do is we're going to zoom in one time further. And we're going to actually look at individual clouds forming in the Radcliffe Wave in 3D. And we're going to do a few things. We're going to actually characterize for the first time the 3D spatial topologies of molecular clouds nearby. But we're also actually going to measure their radial density profiles in order to sort of get at the physics that's shaping these clouds on parsec scales. Okay. So this is Perseus molecular cloud again, and I'll show you what Perseus looks like out on the plane of the sky in a little bit. But there's a few steps that we take to analyze the topologies. So first, what we do is we're essentially taking tools that were originally designed to study clouds in 2D on the plane of the sky, or in numerical simulations, or in position velocity views of the interstellar medium. So based on spectral line mapping, where the third axis is not distance but velocity, and sort of we're reworking them to actually be able to be applied to observations of the 3D spatial distribution of dust for the first time. And so we're applying this new code called, not new code, but a revamped version of an old code called PhilFinder, which is actually produced by incoming SMA fellow Eric Kosh. So really excited to have him here for the coming years. But essentially what we're doing is we're essentially extracting the topological skeletons of all of the nearby clouds at 1 parsec resolution. You can see that's what the skeleton looks like for this cloud. And it's actually colored by distance from the sun, and I'll show you that in a second in an interactive view. But essentially what we've measured for the first time in 3D is the radial density profiles of the clouds nearby. So essentially we're measuring how the gas density drops off as a function of distance from the spine, which can tell you something about the thicknesses of clouds, but also about the various forces, external pressure, gravity, so on and so forth, that are shaping the topologies. So this work is still in its very early stages, but something that is pretty exciting that we think popped out right away is that if you actually model the profiles of these clouds, they actually favor having 2 components. So they actually favor having like a sort of a denser inner envelope with a narrower amplitude, so like an inner envelope. And then they also favor actually having a much broader, lower density outer envelope. And so they favor, all of them favor having this type of profile. And it's potentially very exciting because it could mean that we're actually tracing 2 different phases associated with the dust cloud. So like a lower atomic phase, we know all these clouds have atomic envelopes, and then potentially like a more diffuse molecular phase towards the inner regions. And so if this is true and we can verify this, we could say that we're actually tracing the H1 to H2 transition potentially in local molecular clouds. So I just want to show you this star forming region in a little bit more detail. This is, again, Perseus. And so all the people who attend Star Formation Journal Club in this talk will know about Perseus. But just as a recap, Perseus is one of the most famous nearby star forming regions. So you can see Perseus here in 3D. This is, again, the 3D distribution of dust in XYZ space for Perseus. And I've shown you overlaid the skeletal topology, the spine that we've computed for this cloud. And it's colored by distance. And then we've projected that back on the plane of the sky. And you can see essentially how Perseus looked before in 2D dust. So the background grayscale, that shows you sort of the common way that we analyze molecular clouds nearby using 2D dust emission or dust extinction. But now we're actually able to say to very high precision exactly where your clump of gas or your core, your YSO, your protoplanetary disk lies in a molecular cloud, and how much depth it spans along the line of sight for the first time. And in particular, I just want to show the topologies that we've analyzed for the clouds. So this is the inner topology, which you think is like the inner envelope of the clouds, and this is the outer envelope. And so we now know exactly how those project back onto the plane of the sky, and we can actually compare them and knit together other information from other tracers like CO or H1 or 2D dust to understand for the first time in 3D and in 2D the masses and the densities and the lengths and the thicknesses of clouds, which is really exciting if you've been studying these local regions for many, many years. And so we've done this sort of analysis for many of the most famous nearby clouds. We've done it for 10 of them. Let me show you right here. So we found their skeletal topologies. And we also measured their radial density profiles for all of these clouds as well. And a few things pop out. So the first thing is that all of them also prefer this inner and outer envelope. So again, potentially indicative of like an atomic envelope and like a diffuse molecular inner envelope. But the implications for that extend beyond just the radial density profiles. So to wrap up, I just want to summarize what we've been doing at small scales. So we can actually characterize the spatial topologies of the clouds within 400 parsecs at 1 parsec resolution for the first time. And we've known that molecular clouds are filamentary at very high densities for quite a while, for about 10 years from Herschel. We're finding that even at lower densities that the clouds really prefer to be filamentary, even at densities less than 100 particles per cubic centimeter, which was not known before. And then the other thing is that we see that these density profiles favor the existence of these inner and outer envelopes, which we think we've ruled out being an artifact of the modeling, and we think it is actually real. But whether it is a phase transition is too soon to tell. But either way, we've provided the first measurements of the thicknesses of clouds in 3D. We've provided measurements of the outer and inner envelopes of the clouds. We've also applied a couple other different models to describe the physics of what's happening here. And we're finding there's an average ratio of about 3 to 1. And so we have to essentially invoke some theories to explain why that would be true. So we're going to look at some future analytic models in the coming months and also compare it in numerical simulations to try to explain this. But I just want to conclude by saying that I think it's a very exciting time to be studying the 3D structure of the interstellar medium, either from an observational perspective or from theory, because really this is only the start. And as you add in more and better Gaia data and you add in deeper photometric surveys, you can get higher and higher resolution views of the interstellar medium. And as you bring in other tracers of the gas, so spectral line cubes and young stars, you can really begin to trace and understand how star formation is happening from scales of kiloparsecs all the way down to parsec regions inside molecular clouds. So with that, I just want to thank you for your time. Thanks.
Thank you, Catherine, so much for the great talk. I guess I will take a host's privilege to ask the first question. Just want to remind everyone to please post your questions either in the Zoom chat or on the Slack channel. I wanted to kind of follow up on exactly what you were saying, that future Gaia data will provide improvements. My question is exactly how much of an improvement can we expect, especially now with the early data release 3 being announced to come out on December 3rd. So it's kind of very imminent.
Yeah, so the incoming data release from Gaia, so it'll definitely improve the parallax measurement. I think will improve like by a few tens of %, I think. But I think the bigger gains is in the proper motions will get better. And then in the upcoming release from Gaia Year 3, we'll actually get lots more radial velocities, which is not necessarily important for mapping the 3D distribution of dust, but it's really important for understanding the kinematics of the young stars in these regions. So essentially what happens is that we know that the Radcliffe Wave is gaseous, right? And so there's young stars in the Radcliffe Wave. And we know that the young stars should inherit the motion of their parental cloud. And so the more radial velocity measurements that you have for the young stars, the better you can actually characterize the motion of features like the Radcliffe Wave in 3D. And so we think we'll be able to better characterize actually not just the distribution of the dust, but actually the kinematics of the gas in the Radcliffe Wave, which will be important for constraining its origin. And so that's something that Alan, our new student, is planning to work on when that comes out.
Awesome. We have a question sort of along those lines. John Raymond asks, how does the filamentary geometry relate to the magnetic field direction?
That is a great question. And something that I actually haven't looked into, but there's the possibility to do this a lot better in the future. So we do note that, so not necessarily in Perseus, but we have looked at like starlight polarization and also magnetic fields as traced by Planck and dust emission. And we're finding in particular that some of these larger structures, in particular structures that are bubble-like, that you see the magnetic field sort of threading the shells of these clouds in 3D. But one of the things that I didn't actually get to touch upon, but will be super significant in the future, is there have been recent results by one of our collaborators named Susan Clark, who many of you may know. He's actually mapped the 3D structure of the magnetic fields in PPV space, so in position velocity space using H1. And so in the future, we should be able to actually knit together information on the H1 structure of the magnetic fields as a function of velocity with the 3D dust. And so in the next year or two, hopefully we'll actually have a much better answer to that question and actually be able to map not just the dust in 3D, but also the magnetic fields, in which case I can give you a much more thorough answer then. But we're still in the very beginning phases of understanding that.
Yeah, that's very exciting. And just like this intricate structure of the clouds, yeah, there seems to be a lot of information there. And Morgan Loud asked if you could talk more about the observed damping of the sine wave feature. Is this thought to reflect internal dissipation in the gas? If so, do we expect associated shock features? And is there any way to see that?
That's a great question. It's also a question I can't give you a totally full answer to. So one of the things that we want to look at is whether we also see the damping in the stars. So I don't think this is a shock feature. I think that but the way to tell this in particular is, so Gus Bean, who might be on this call actually, is he's working on these new simulations called Milky Way in a Bottle, where he actually will be able to model the stars and the gas, and will actually be able to collide things with our galaxy and figure out whether with this sort of collision, you would expect this dampening to happen. And so right now, given that we really only know the morphology of the gas, and we actually haven't done any detailed comparisons with simulations yet, and there really is no simulations actually modeling the gas phase of this sort of damping pattern. I think it's too soon to tell, but we should know again when we have better kinematics from Gaia and we actually have these detailed comparisons that we're really excited to work with Gus and Lars on in the coming years. Yeah.
Sounds great. This is kind of a great way to close the seminar for theory and computation and connect it back to the kind of physical simulations of star formation at those small scales. Looks like we are kind of out of time. If you have more questions, please send them to on the respective threads to Karan and Katrin on Slack. Thank you all for coming. Thank you to our speakers for sharing these wonderful results with us. And yeah, looking forward to hearing more from you in the future. Thank you.
Thank you so much.
Thanks for hosting, you guys. It's great. Thanks.
Bye.
Thank you.
Bye, everyone.